Excellent. So welcome, everybody. Good to see you. So it's my pleasure to introduce Dr. Joe Michail to the BHI today.
It's also weird to hear.
I know, right? Yeah.
Hasn't sunk in.
You'll get used to it. Hopefully. So Joe received his bachelor's from Villanova while working on the variability of low metallicity Cepheids in the Magellanic Cloud before moving on to do his PhD at Northwestern, working on variability in the galactic center with Farhad Yousefzadeh. He's now an NSF postdoctoral fellow just up the street at the CfA, where he is tackling a multi-decade statistical analysis of radio and submillimeter variability of Sagittarius A star. But today he's going to tell us about much higher frequencies, I believe. And so it's a great pleasure to host you here, and I'm looking forward to hearing your talk. There's still a few slots for dinner, by the way, so please don't be shy and join us at the painted photo. Take it away, Joe.
Thank you. Thanks, Daniel. Thanks everyone for coming. I'm sure the prospect of having lunch after this had no reason for you being here.
That's the news.
The new one, right? So I have the pleasure today of talking about this JWST MIRI results that just came out last month. We had a press conference also last month at WS, and I'm honored to be talking about this on behalf of all my co-authors. The ones highlighted here in bold are young career, early career, with myself, early career scientists, and they really helped a lot, especially Sebastiano, who led the paper. I mean, these are his results. Now, the nice thing about being at BHI, I don't have to explain what Sagittarius A star is. I think everybody at home in this room knows what Sagittarius A star is. They know that its mass has a low mass, like 4 million solar masses or so, which, because its gravitational timescale is only about 20 seconds, it has rapid turbulent variability in the accretion flow, and which can produce variability in its light curve, especially on hourly timescales. Now, these flares are not always the same. They have changes, but we can kind of group them into three large categories, or three properties that we can look at in terms of three large categories. It's not going to go. Okay, so the three general phases of Sagittarius A star's flares is that they're time delayed. So if you observe in a multi-frequency sense, multi-wavelength sense, your higher frequencies will come first, the peak of the emission, and then which cascades to lower frequencies. Depending on where you are in frequency space, this could be seconds, minutes, hours. They're also polarized, and their polarization changes on timescales similar to the total intensity variations. Which means, so that many studies, again, with people here, have shown that this change in the linear polarization, and as it changes with the total intensity, they're probably correlated, which kind of gives signatures of orbiting hotspots around Sagittarius A star. And then what I'll mostly be focusing on here is the multi-wavelength aspect, which is kind of related to the time delayed aspect, but more general. So in this plot here, there seems to be a correlation between the X-ray light curves, which are in some weird yellow-ish color, which we see a dip at the 8 to 10 gigahertz range, so about 3 centimeters radio, just as the infrared peak, or just as the X-ray peak comes up. Now, on the topic of multi-wavelength, the mid-infrared, where we are about 5 to 28 microns, lies at a crucial position in the SD of Sagittarius star. So again, people in this room might recognize this plot from the EHT paper in 2022, where this is showing the average flux of Sagittarius star across multi-wavelength frequencies. So in the radio, we have this really nice parallel with a spectral index of about 0.33. You get to a point around 230, 345 gigahertz, where you have the submillimeter bump, just as where the spectrum will start to turn over. And this peak changes back and forth because of the low energy cutoff of the electrons in the region. What's it all 2018 and 2021 showed that. And then you get to this colors are really muted. You get to this kind of desert area where there are only upper limits on the variability, how bright this is, how much it varies. 3 sigma, 5 sigma upper limits. You get to this tiny region of stability in the near infrared, where we have JWST, Keck, gravity, Hubble, all these kinds of things we can actually observe variability. Then again, we have this desert caused by gas and dust between us and Sagittarius A star until we finally get to the X-ray, which is very variable. And this is the general region of the mid-infrared, which have not detected Sagittarius star at all. So the galactic center is difficult regime, right? We have us, between us and Sagittarius A star, there's about 26,000 light years of gas, dust, stars, aliens, whatever between us and the source. So this is a Spitzer image showing the couple of degrees-ish, the central molecular zone, where a lot of stars are forming outside of Sagittarius, forming in the galactic center. And if we zoom into this region called Sagittarius A, of course, we have the mini spiral surrounded by a lot of different point sources. And then at the location of Sagittarius A star, there's no point source. So this was one of the latest observations taken with Visier at 8.6 microns, where there's absolutely no detection that they can make of Sagittarius star or its variability. To give you some context, also, the average extinction in the galactic center at these frequencies, at these wavelengths, about 1 to 2 magnitudes. So you have to correct a factor of about 3 to 6, depending on where you are, and it's very spatially variable, especially as you go towards true center of the galaxy. So why haven't we seen anything? We've looked at we've put some of the most powerful telescopes on the sky to observe Sagittarius A star in the mid-infrared. What's happening? Well, the kind of the latest and greatest up until JWST is that the flux density of these flares at 8 microns would be about 5 millijoules. Point source. And everything around it much brighter than this. We're talking hundreds of millijansky, especially with the mini spiral and the gas and the dust, which are much brighter than Sagittarius A star itself. And one of the issues is that we've been limited to ground-based observatories. There really hasn't been a high sensitivity, high angular resolution telescope in the mid-infrared for a very long time. I think IRAS or SWAS was kind of the last one in the 80s, the 90s. So we've had kind of this desert, effectively, of mid-infrared coverage space. And because of the gas and the dust, you have to kind of trade off between photometric sensitivity, stability, making sure that your detectors are stable enough to not impart a variability onto Sagittarius A star that's not intrinsic to it. It's caused by variations in the detector itself and spatial resolution. So how do you separate a source? How do you have enough sensitivity, enough spatial sensitivity to separate a source from the surrounding background? None of this was possible until JWST and MIRI came. So over the last 6 months or so, I've learned a lot about infrared astronomy or mid-infrared astronomy. And so now you have to also. So JWST MIRI is one of 6 or so instruments on JWST. And MIRI itself is made of 4 different instruments: mid-resolution, medium-resolution spectroscopy, low-resolution spectroscopy, coronagraphy, and regular imaging. That's the one. But this MRS, this mid-resolution spectroscopy, is the only one that can observe at multiple frequencies simultaneously. So this is the coverage of MRS, the MIRI MRS. We go all the way from 4.8 microns all the way up to about 28 microns. Which, if you're not looking for time variability, you can switch between the different filters and get full coverage. The issue is if you're trying to look for flares, you don't want to switch between frequencies. You want a nice, long, continuous coverage. So the best we can do is we have to choose the short band, the medium band, or the long band. And that sets which filters we can actually observe at any one point. For our case, we took the short band, which covers 4.8 microns for a very specific reason, in that we've seen flares at 5 microns before. Spitzer, albeit it didn't have great spatial sensitivity, colleagues up the street have been able to detect, really beautiful long-term light curves at 5 microns. So by choosing 5 microns, we kind of know what we expect. If we see flares, it's not all of a sudden that we're higher frequencies and we have no idea. We can't separate the background emission from gas and dust.
So based on the spectrum you showed us, is the signal to noise ratio getting higher at short wavelengths or where is the best?
So the best, your spectrum at the mid-infrared, your variability spectrum is negative. So you technically have the brightest flares at the highest frequencies. However, the gas and dust also has a positive spectral index.
So who wins?
The dust always wins.
Okay.
I wish I would have known that before I chose my undergrad project. But, so the best way to do this is because you have to when you go to lower frequencies, the dust subsides, and your point source sensitivity also increases, your PSF decreases. So 5 microns is actually the best with JWST to look at to detect flares. And because we know about it, we have a general sense of where everything is in the galactic center. But things aren't so easy. So when you typically think of an imager, you think of pictures from JWST, you think of an actual image. This is the galactic center for MIRI MRS. What this is an integral field unit. So you're pointing your telescope at a specific location in the sky. What you're getting out is this slitted spectroscopy, where each of these slits has something to do with your sky position. And the sky position is not a trivial equation. You can't say, I'm going to go from this pixel to that pixel. I'm going to be right next to each other. You could be the opposite side of the sky, the opposite side of your field of view. This is a very complicated equation, effectively, that's all built into JWST. And this is your wavelength axis. So there's 2 things going on here. You have your first channel, you have your 2 separate channels, channel 1, which is a 5 micron, and your channel 2, which is 8.9 micron. And then you have spectroscopy on top of it. So this goes from about 4.8 to 5.6, and this goes from 7 microns up to 9 microns. So you have this double spectroscopy effectively. Now these straight lines here are specific bright sources in your field of view. A spectral line would appear as a horizontal line, but anytime you see a vertical line, you see a true single source. We don't like this. As astronomers, we can't think of, I'm sure some people can, but us, cannot think in terms of IFU space. We have to think of spatial space. Luckily, the pipeline, the JWST pipeline, has this built in, where it takes these IFU cubes, puts it into this gray box. Now, I'm not calling it a black box, because we kind of understand what's going on, but we kind of don't. So, gray body, not black body. What we get out are true spatial maps of the sky. So somewhere in here is Sagittarius A star. Actually, I think that's source itself. And then you have the edge of the mini spiral, a couple of the IRS 16 sources. Yeah.
Oh, sorry. I just wanted to make sure I'm understanding it right.
Yeah.
So each one of those strips would then correspond to one of the pixels in that image?
No.
Oh, okay.
So your IFU is subsampled, it's not Nyquist sampled. And in the pipeline, again, the gray body or gray box, it bins. Yeah, we don't know how this works. It takes certain pixel X's and bins them to make spatial images. So if you're within, I guess, half a pixel, it kind of moves your flux to certain parts of the map.
You can test that on calibration sources.
Yes, so the nice thing about this, right, is that because these are sources, single sources, which are probably one of the IRS 16 sources because they're not diffuse. Right, this, if you have some sort of spread, it probably tells you extended structure, whereas a single line tells you single point source. So if you figure out where this is, right, you can test to see if it's at the center of a single source or not. And yeah,
So when you say we don't know how this works, is it that there are fundamentally unknowable systematic effects inside JWST that are being folded into this, or is it just that this is underexplained in the user manual?
this is us not wanting to read the user manual.
Oh, okay. Right.
So we have, we asked one of the ESA liaisons in the STSCI office in Maryland, Maka Gerson-Marin, to join us to help us understand what's exactly going on. The actual, what we'd like to do is not even have to do this, not even have to go to this map, because this is a very time-intensive and computationally expensive process to do. What we would like to do, and what we've actually done, is in the kind of last part of Sebastian's paper, we've extracted the light curves directly from the IFU plane, which takes a little bit of work going back and forth to actually get the location of Sagittarius A star, because there's also issues when you're talking about WCS and being on the right position of the sky. But we would like to just use this IFU space. We don't want to keep making our computers chunk away for limited. Yeah.
So you're going back to the true data. You're not getting this derived map from this gray box. But in terms of fitting, do you have enough data? If you just wanted to get the light curve of Sagittarius star, is this an overdetermined problem? Is this like how many parameters in your model ultimately, and do you have enough data from the IFU space to really lock into the light curve of Sagittarius star?
Yeah, so we're effectively collapsing each channel into a single filter map, right? And then each one of those filter maps has time steps, step by step by step. So this is just a single, you could think of it like a single UV data point, right? And when you try to get the light curve of a UV data point, you get a bunch of UV data points, pin them together, and then get the light curve, right?
What's the angular resolution that you have?
The angular resolution, so in a perfect world where you have to move the telescope to 4 different positions to resample the PSF, you get between 0.3 and 1 arc second.
That's terrible. Because there are many stars inside of that.
Yes, so what we can do is that we don't look at absolute, we don't yet have the absolute flux of Sagittarius star in the infrared. We do a relative correction. So we take some baseline and say from this position, we're increasing by a couple millijansons. Everything right here, right now is relative, or what I'll show is relative. But answer your question, Shel, I'm sorry.
I'm gonna wait.
Okay.
I'm sure it's just around the bend.
That's what you're thinking. Okay, so these are what data we use. Then we have a bunch of time slices for all 4 channels. You take the position, the light curve in the position of Sagittarius star, and well, we detected it. So on the top here is a little inset of Sagittarius A star, about a 1 arc second inset at each of our 4 channels. And then this blue emission around it is just the mini spiral and other sources around it. And this is the time map. So this is the time, the GIF. That's the right way to say it, not GIF. So on the bottom are the light curves at the 4 different frequencies. Stopped. Again. So as we're stepping through time, this 90-minute observation, we're seeing that Sagittarius star flares at all 4 frequencies. It's very clear detections, right? This isn't noise. You have, I think your individual sensitivity on a single point is about 10 signal to noise ratio or so, 10 or greater. Yeah.
What is the 0 point of that flux? Clearly, it's going below 0 in some places.
So because we have to do this relative subtraction, we take a bunch of reference points around Sagittarius A star with a that are within 10% of the flux of Sgr star itself. And we use this to correct any residual time ramps, like how the drifts in your detector, but also we can get a relative sense of how much flux we need to subtract. And then again, we take the lowest point in our light curve and make it 0.
You didn't.
Yeah,
I think it's just the point.
No, no, look at the right. That guy is definitely
Right,
below
right.
0.
The bottom right.
Oh, this one.
That one, yeah, right, or any of these guys. There are
Make this
places.
plot.
Yeah.
That's what I'm gonna chalk it up to. But because this first point that you can't see whatsoever, forget about these.
Okay.
This first point is just because you have the first time step, which really needs to get thrown away, because your detector is still getting used to things. Persistence or whatever the case is.
Yeah.
Yeah, but that's a good.
I was looking actually at this point, this guy is definitely below this 0, and I think as Daniel said, some of those are worse.
I didn't make.
what is the scale in solar luminosities? So just compared to a star, I just want to see, is that much bigger than a star can produce, or is that much smaller than a star produces?
You know,
Because stars vary,
I was gonna calculate this too. I said someone was gonna ask this. Because this is reddened, I don't think that we have a good sense. Because the reddening is, the extinction is so variable in the inner. Differential extinction is so massive in this area. I don't think we have a good sense of the actual scaling. So this is reddened. This is not de-reddened. Because we're not doing anything again in terms of absolutes, because there are just so many unknowns with the relative scalings in this.
On the right two, if you look up in the maps, you still see some residual stuff. Is that just noise, or are those really other variable sources within the field of view?
No, it's definitely noise. So the stretching isn't linear. We've really had to make it a lot larger to really show this, especially for the channel 4, because of just the dust around it. So you're really seeing low level variations. There are in channel 4 there, the drift is larger, but still your sensitivity is sub 10th of a percent statistical. The variations. This is really a stretched artist impression of what's going on.
I think I could have been tracking this from the previous slides. What are the units of the maps?
Oh, sorry, arc seconds.
Thank you.
Yeah, so centered on Sgr stars.
Right.
Excellent. Yeah. Very small. Absolutely. You want to see it again?
No.
But, we have a ton of, come on, now this is gonna go, okay. We have 4 wavelengths, a bunch of radio astronomers in this room. What do? We fit a spectral index, right? We use power law. That's a natural thing we can do when a bunch of radio astronomers are on this paper. So we can fit a spectral index, right? For the first time, not only do we have the the relative changes in the spectral index, how that varies in time. What we do is that we kind of, not a hand wavy way, but we normalize everything to a single point in time. We make that R1, which takes the variable, which takes the extinction out, which takes any other background sources out. And what we have is that we have a relative map, which collapses all of those unknowns. And what we can make is a change in the spectral index as a function of time. So we have changes in flux and changes in the spectral index. This isn't absolute, right? We don't think that this is a achromatic flare, or the initial parts of the flare are achromatic. The only thing we can say is that their relative changes are achromatic. We see a sudden shift, and then you see a change in the spectral index of about a half. If one day we ever figure out what this background is, we can add all this up and actually get a true spectral index variation. How much does it change over the flare? Now, what's so special about this is that we now have the possibility to study the change in the spectral index in the infrared, the mid-infrared. And now this has been possible with radio, submillimeter, and X-ray observatories for a while now. So not only do we have the flux, but suddenly we can see how the changes in the flare of the spectral index occur over a wide swath of your frequency, of course, around your electromagnetic spectrum, which gives us another way to determine what the relationship is between the lower frequencies all the way up to the higher frequencies. Just, really special, at least for me. But, what's a party without some friends? So not only did we use JWST, we got 3 other observatories. We convinced them to observe with us. New Star on the bottom, which is high energy X-rays, Chandra, everybody's favorite X-ray telescope, no offense, New Star, and on the bottom, SMA. So SMA observed at 220 gigahertz. I'm sure you all know what SMA is, right? CfA's telescope, SA's telescope on the top of Hawaii, or top of Mauna Kea. Now, New Star and Chandra didn't see anything whatsoever. It didn't detect an X-ray flare. But the SMA did detect one peak, delayed by about 10 minutes relative to the last infrared peak here, and it changed by about 400 millidrans at 220 hertz. I'll get back to this a little bit towards the end. Now we get to the fun part, which is modeling. I want you to give me a little bit of artistic freedom because I drew these. It's the first time I've ever drawn something for a presentation, all right? So don't be mean.
Oh, nice.
Yes, Joe. Sgr A star is not orbit. It doesn't spinning at negative prograde, maximal prograde. Yes, I know the ISCO doesn't go all the way down to the event horizon. I get it. For our, third grade impression, Sagittarius A star has some region, call it a flux tubule, call it a flare, a hotspot, what have you, that has carved out a local hole in your accretion flow, and we're going to inject electrons into this region. This is our basic picture. It's orbiting on a radius r, and have this flare has size RF, which we hold constant. More drawings. We're going to use a Gaussian injection in time of electrons into the source, so we can fit for the number of electrons we can put, the width of this injection, the time it's maximum, and just for fullness, we've assumed a power law of electrons, what the energy index is, -2 in this case. So these are mainly everything that needs to go into this model to fit this flare.
You need the magnetic field.
Magnetic field, yes. That's because it's powering synchrotron emission, we need to fit for a magnetic field. Our free parameters are those 3 for the Gaussian injection I just mentioned, the magnetic field strength inside of this flare region, and also the orbital inclination of the radius. There's one other parameter which gives you the orientation of the orbit in the plane of sky. I never check orbital dynamics out of it. Yes.
Yeah. But why did you choose gamma to the -2 instead of a free index? Because you have spectral index information.
Right now, so P of 2 is roughly what's been seen in the literature. So we also did a fit with P equals 3, just to give some sensitivity. For this case, we just chose a nominal value. It's, but we can absolutely make that a free parameter. You probably get more degeneracy with your parameters because you want to fit more in your spectrum, and Your injection profile, I think, would be degenerate then, because if you make it more steep or less steep, it will change the number of electrons you need to impart. But I think for this first case, P equals 2 is.
Two is a dangerous
It's a
value.
strong shock.
Well, no, but I think, but you want to be a little above 2. 2.5 is good number, 2.2, but yeah, but anyway, it doesn't matter. But if you want to look at spectral index,
Yeah.
then you need to relax that choice 2.
Can I ask one other question?
Yeah.
So are you pinning the magnetic field orientation to the orbit inclination? Like, is it just assumed to be vertical?
I think it's assumed just to be along your inclination axis.
Sure.
Yeah, so your choice of inclination. There's no Stokes V, so I
Sure,
don't think we
sure.
necessarily care about it. And what we've done also is, we've assumed the size, we've assumed the injection, the parallel injection of electrons. As this is orbiting, we take into account Doppler boosting and deboosting because we're fitting orbit. And also gravitational redshift is one other piece of the pie. We don't do lensing because our previous results, Sarah's results, gravity results, the inclination is low enough that we don't have to take into account lensing. You know,
So you're saying you're assuming a face-on geometry.
more, so we fit for the inclination as a free parameter, but
But
just
you just said that.
just from previous results.
Assuming it's a moderate. But I think the claim, right, is that the radius is large enough that as long as you're not sitting exactly edge on, you're basically seeing an unlensed block.
Yeah, but that's,
Oh, I see, so the radius is far
Um,
away.
it's left as a free parameter in our modeling. I think so from gravity, I've seen radius orbits of about 6 Roche.
Has gravity really seen orbits?
Let's say hotspots on orbits, we think. Now, you could-
Really?
That's the claim.
That's the
The
point.
centroid is moving.
Yeah, you can see the centroid.
Centroid moves, that's an
moving. I
orbit.
think it's a far cry from an orbit being observed. I am telling you. This is me telling you.
The first author is on the gravity team, eh?
Well,
Oh, right.
I'm sorry, I'm saying something serious, which is that you're assuming something for
First-
gravity.
yeah.
And I'm saying that the gravity result is interesting, it's very model dependent.
And gravity, what was the wavelength there?
This is J and K, I think 2.2 microns.
Okay, not
VLBI.
too far, it's a factor of 2 from what you're doing. Yeah,
Roughly.
okay.
But even from VLBI results, right, we have some estimate of what the inclination is. Right. So it's
Well,
not.
there
very
are
much
some models.
Sarah's model, right. Inclination from the VLBI, 860 hertz. We have a general sense of, we know it's not this way, right, so we know that we're not seeing generally behind black hole or lensing it might be a factor.
So you're fitting light curves, right?
Yeah.
And you're only fitting total intensity. or
Total intensity, yeah.
Total intensity.
MIRI
So
has no.
I think that the main concern for the effect of lensing in this case would be when you're getting to the higher end of inclination, you're going to get large variation across your light curve.
Mm.
But my guess is that you're getting relatively low inclination values preferred.
I think we've found about 17 degrees plus or minus.
17.
Oh, no.
My goodness. Which object are we looking at?
Okay, all right. I need to see how this plays out.
Because we're not using polarization, but we might soon, the model parameters are very degenerate with each other. So we can say 17, but when we take into, we don't have that good of an estimate on the inclination.
Sure.
Just yet. All right, so this is our fit. The points are the actual MIRI observations. The 3 colored lines are the best fit models. Your dotted line is your injection profile. And the dashed line is the Doppler boosting factor, or a normalized Doppler boosting factor showing you where in the orbit this flare is. We get values, maybe not the inclination from this conversation, but we get magnetic fields about 40 Gauss, which generally match what we see in the literature between 30 and 70. Orbital radius, again, model dependent, 6 Schwarzschild radii. A number density of 10 to the 7, which roughly matches again what infrared in general has seen, observed just from microwave themselves. So we're getting values that are kind of consistent with what the literature has set up for.
How is the field compared to equipartition? If you were to take the temperature, or if you want compared to the accelerated electron population, because physically speaking, at least in the interstellar medium, it's close to equipartition.
I don't think that
You didn't compare.
we didn't. Yeah, we didn't
Is it
compare
close?
that.
Yeah, the field,
No, but this
would be dominant.
For these values,
Yeah,
it's close to equipartition.
or actually field stronger.
Stronger.
Yeah,
The betas, well, I guess
By how
depends on which value.
but it would be 40
Oh,
Gauss
the
is
unity. No, a bit much bigger.
beta, plasma beta would be less than 1.
Less than 1.
Yeah.
Oh, okay, good.
Now, we've labeled 3 different phases down here to show kind of what the dynamics of this orbiting hotspot, this orbiting region, I shouldn't say hotspot, is what's going on.
Oh, wait, sorry.
Yep.
What's the fit in this curve? Is it
The
the
fit are
solid line?
these solid lines.
Okay, thank
Yeah, the data direct from JWST is
Sure.
So in the first phase, we get an achromatic increase in the flux. All your light curves or your data points are increasing at the same rate, which gives you this, moderately within the error bars, achromatic increase in the flux. Your spectral index hasn't changed yet. You're inputting electrons, the first set or the first portion of electrons, which is increasing the flux. You have a Doppler boosting towards us according to the fit, which is increasing the flux even more. So you have this kind of 2-tiered increase, so cause the increase in the flux. In your second phase, things start to go differently. So what I'll call phase 2A, in the first part, you started to deboost. You're on the opposite side of the black hole, it's moving away from you. At the same time that you're putting in your rate of injection of electrons has started to decrease. So you get this kind of battle between the maximum number of electrons or the most electrons that you've put in, fraction of electrons you put in, competing with your Doppler deboosting, which gives this sort of decreased, flat-ish feature in the light curves. But you also notice that in the spectral index, you suddenly got a change in the spectral index about -0.4, which occurs around t equals 30. And around t equals 30, that's where you stop. Most of your electrons have been injected already. Sorry. So then you're battling the synchrotron cooling with the injection of energy, and your synchrotron cooling has started to wane, causing the change in your spectral index, your sudden change in spectral index. Then on the opposite side, right, so the rate of the electrons that you're putting in has rapidly started to decrease. You're still Doppler boosting towards you again, but it's not enough to take over and your flare fizzles out, I'll call it. But still, because you're not injecting as many electrons, you still have a flat spectral index. Relative spectral index. And this is generally consistent with GRMHD modeling. So on the left here, this is a GRMHD model from Ruperta et al. 2022, which shows this flux tubule. So what we think, and what our magnetizations, the proton magnetizations kind of match, is that as you're in the accretion flow, your magnetic fields are tangling up, you can get a magnetic reconnection event, which causes pinched fields to turn vertical. Everything in an accretion disk is ionized, and ionization loves magnetic fields. It streams without them and creates this vacuum gap flux tube. And because you have a difference in contrast between the densities, you get rarely Taylor instabilities at the edge of this tube, and electrons flow in, creating sort of a hotspot, which then orbits. Now, because we have fixed in our initial modeling, we've specifically fixed the size of the hotspot. If we want to get any sense of what the magnetization is doing, what we do is kind of take a uniform prior between 0.8 short shade radii and 2.3 short shade radii for the size of the flare. We vary this, we recalculate our fits, and we get an estimate of the distribution of your electron and your proton magnetizations. And Ruperta et al. Generally find that 0.1 and greater is consistent with this GRMHD flux tube modeling, which in most of our fits matches. Now, what this doesn't take into account are our error bars on our model parameters. These are just the center, the 50% values, which are used to calculate this. So there's probably, larger error bars. But there are larger error bars that we're not accounting for on this plot.
Can I ask a question? So there were 4 facilities looking at this. You've got JWST, 2 X-rays, and SMA. You didn't say anything with the X-rays, so this is not producing any
It
X-rays.
didn't produce any X-rays, which sets an upper value for the upper energy cutoff.
Okay. But for this SMA, you can get polarization from that, right?
Yeah.
So if you, with the magnetic structure you're proposing here, what would you have seen in the radio for polarization, and did you see that?
I'm working on it. So that's my, we have the SMA polarization, the polarization was observed. We're getting to that point to actually use the polarization without having to use IDL. Constant is so close, and getting polarization to work for SMA this close. This hopefully. That's when I'll run. But right now, we couldn't say anything about the magnetic field configuration because we're assuming a orientation of the magnetic field, so it really wouldn't be. We're not doing any sort of total or full Stokes modeling of this. We're just doing a single Stokes I modeling, or yeah, there's no full polarization, anything in here. What we think, speculative, is that because this is orbiting, or we see this orbiting, we should expect to see QP loops in the light curves. On the top, yeah.
Well, I have an unrelated question, but sorry. So in these distributions, I just want to understand how you're constructing them. So is your blob a one zone model, or have you, okay, so you're not like resolving the blob.
No.
So these distributions follow from having uniform values for everything except the electron energy, is that right?
So, yes, you're keeping the power law distribution constant E -2, or if that's your initial injection, and you allowed cooling by synchrotron radiation effectively. But you're not changing anything about P in this.
I'm just trying to understand what parameter or property of the blob is changing to cause different points in this distribution to appear, because you created this.
You're varying the size of your radius, which changes if you have, let's say you have a constant number of electrons, right? If you increase the size, change the size, your electron density changes.
I see, but you said that this was a single fixed value of your model.
In the initial fit,
I
we
see.
fit a single fix. So these light curves are single value. Assume short shade radii is 1. If we want to get anything, if we want to look at the magnetization of the electrons and the protons, then we vary this. But we don't show these.
I see, but you're not fitting, you could in principle fit the size of the blob.
You could, yeah.
I see.
You just you add more parameters and
I
everything.
understand, yeah,
you get
okay.
more and more. More degenerate. But on topic of SMA, we saw this 400 millijansky increase at 220 gigahertz with SMA, but we can't confidently say if it was by chance association or a true connection with the mid-infrared. Because we don't have any lower bound on the electrons, the lower energy cutoff of your electron spectrum. So what we've done is we did two tests. The first is we take a nominal value of your gamma min of 5, which is 2.5 MeV. We fit the model and we predict what the 220 gigahertz light curve should look like. So in black are the actual observed SMA values, the dots, and then the straight line is what we expect from the light curve. And they match pretty well. The issue is that if we change it to a gamma min of 10, right, so we're going to 5 MeV instead of 2.5 MeV, we no longer produce any submillimeter emission. We go from 400 millijanskis predicted to something like 50 millijanskis, so 40 millijanskis predicted. Because we don't have any good sense, well, we don't have a sense of what this lower energy bound is, we don't make any claim if the submillimeter is true. The submillimeter increase is true, is it really causally connected to the mid-infrared, or is it just by chance association, just some kind of variability? We can't make a statistical claim because the change in the spectral index between the two models are not, but there's no statistical preference. We can't make a statistical claim, and there's no lower frequency data to say this is where the minimum gamma truly is.
So,
Yeah.
a quick question. So under the parameters of this model, there is really no time delay, right, between the infrared and submillimeter by definition, because it's the same electrons that are radiating in all of these bands. But I thought you mentioned that there is some evidence of delays.
We did see about a 10-minute delay in the actual the model itself, or you don't see a time delay in band in the spectral in the mid-infrared. But at least from my vantage point, there is a small, it's not great. But again, we're glazing over a lot of the parameters, fixing a lot of the fits. Which, you know, could in principle see.
No, but you shouldn't have any time delay, right? I mean, it's just this one ball of hot electrons producing all your radiation. It's moving around. How can there be a delay?
But you're cooling, right? So if you don't have enough electrons, if the peak of your submillimeter flux will depend on how many electrons are in band effectively for the 220 hertz. So if you're cooling, right, you do expect some delay just from a cooling perspective as the hot electrons cool and produce and increase your submillimeter flux.
Okay.
And because that's a little bit different, because you have to wait a certain time in your modeling, right? So the cooling electrons have to actually cool all the way to submillimeter. You could be in a different orbit position, which might change your Doppler boosting. So it's not a one-to-one comparison. And also you can see here that the SMA might have missed this peak because of looking at a calibrator or off source or an antenna, whatever, a couple antennas went down.
So you're saying that the high energy electrons first are radiating in the infrared and they cool.
They cool, yeah.
And then they start radiating in the, but the synchrotron cooling time is much longer for the SMA, much longer. So wouldn't you expect, why do the curves look like they're the same profile in time?
Your at infrared, you have about a 5-ish minute cooling time of your electrons, where we're 40 to 30 to 70 Gauss at these frequencies, about 5-ish minutes, give or take. So you're cooling, your electrons should have sufficient time to cool to move to the submillimeter band. Right? Because that's
Well, there's a lot to the model, but it seems like the drop off is commensurate with the drop off in the infrared.
I agree. I
don't know.
Yeah. I think we've seen, maybe this is just reading too much of the literature or putting too many priors in my head on the fit. I think the submillimeter nicely matches. Everything that we've expected from other frequencies has matched. Exactly what we've seen, a 10-minute time delay. A nominal.
Well, I think the important thing is that this is consistent with your model, that you take into account the synchrotron cooling in the radio in the model, and I was just expressing a little bit of surprise, because I thought the cooling time would be much, much longer. But that's the way it looks, that's the way it looks.
It's a strong field, 40 Gauss. And many of the estimates probably use a weaker field.
It's the same field for both.
Yeah. But the cooling time depends strongly on the magnetic field strength. Yeah. But I think we should probably now let him, you want to finish your talk? And some people actually want lunch, I think, but
Also,
I'm happy.
we want the last slide also, remember?
This is what I'm worried about. I want to make sure that we actually see the final, yeah,
Okay.
the
So we've
recent data, yeah.
We've talked about polarimetry, Q loops. That's the next step, right? We have SMA polarimetry. This will be a standalone paper. This is what Vilga saw at 220 gigahertz with 2017 EHT from ALMA. X-ray flare happened, and then you start to get these radio loops, QU variations. SMA has the data. We're going to do it. That's the next step in this, to see if we can actually connect the two and see, because if we have polarimetry, we can reduce our degeneracy between the orbital parameters effectively. So we model the mid-infrared and the submillimeter total intensity of polarimetry, and hopefully we can get better values for the better estimates in the orbital parameters. Oh yeah, I forgot about that one. Okay, but one important thing to note is that this is an hour and a half long. This entire thing, this last 50 minutes, an hour and a half of data. We have 21 hours of on-source time still total over April to September. Each one of these has some sort of multi-wavelength component to it, be it X-ray, 86 gigahertz VLBA, which if anybody knows how to calibrate that, please talk to me. There's a lot to do. And to this end, we've actually proposed an EHT project led by myself, Daryl Hager, and Carter Keating to use the SMA data over the 3 nights of VLBI Go data in April 2022, 2024. God, last time I did this on a call too. I started to say 2025, and then Daryl was like, no, 2024, don't get confused. All right, fine. So we have about 70% simultaneity with SMA. And the idea is that if we can use MIRI and SMA and the multi-wavelength, we can get a much better statistical claim, among other things, to see if the two are connected. Okay, last slide. Well, second to last slide. MIRI is not the only one that's looking at Sagittarius A star. If you were on any news outlet last week, you might have seen this claim that we finally understand Sagittarius A star in the near infrared. JWST has solved Sagittarius A star. It really hasn't. However, NearCam put out its first results from 40 or so hours of like 12-hour chunks ish of data on Sagittarius A star between two frequencies, 2.1 and 4.8 microns. I was on the paper, and what I wanted to mention is that JWST is kind of revealing more and more what we didn't know about Sagittarius A star, especially, not especially, in both near infrared and mid infrared regimes. This is the highest sensitivity, longest duration observation of Sag A star at near infrared ever. And you see very small variations. It's constantly variable. There is no quiescent emission. And obviously, with the last 55 minutes, I hope I've convinced you that mid-infrared is another way forward. It's another way of unlocking the secrets of what powers Sagittarius A star's flares. So you've heard enough of me talking. I'm done. I can take any questions. Thanks for listening.
Yeah, so one of the sort of key, I guess, features of your model light curve was this sort of two peak. This rise, the rise before the final fall. But the mid-infrared light curves, when I look at them, look like they have three peaks.
Yeah.
What, do you have any idea what's going on with that middle peak?
So it's the assumption that we only used a single injection of electrons. In the appendix of the paper, we've done a double injection. So we have two different Gaussian injections of electrons into this region, and we've modeled it. Again, I don't think the statistical difference, the chi-square difference between the two is that different. If I'm remembering the table correctly. But this could be caused by a secondary injection. For our first model, our first look at this, we just want to do a single injection of electrons.
Now that you mention it, this bump may be followed by something happening here. So it's not a second injection in the same plot.
Mm-hmm.
It's another location, which is having its own Doppler. I'll make a whole story here. I don't need the rest of it.
I want to see your measures going.
As it always happens, right? The JWST stopped after this one. We have another 90 minutes, I think, beforehand. I think this is the day that it malfunctioned and we lost guidance or something crazy like that. We were supposed to have 7 hours on source and, things and Murphy's Law, and that's not Murphy's Law. Occam's razor, yada, yada, yada. Something happened. Something bad happened. But we have another 90 minutes beforehand. But you're right, we have much longer duration.
Yeah.
than we can also look at.
You first, Jeff.
No, you first.
Oh, fine. So do you expect the noise in the different JWST bands to be correlated?
I think from channel 1 and 2 and 3 and 4 should, if you go back to this IFU, right? Your channels 1 and 2 and 3 and 4 are on the same plane, right? So the same detector that looks at, the same detector has channel 1, 2, and 3, 4 on a different detector. So I think if there's noise, it should only be correlated between the two pairs, I think.
Okay, yeah, I guess my desire to interpret the middle bump as something real, or any bump is real, really, in data of this SNR, is heavily driven by the fact that all the bands are seeing the bump, right?
Exactly, yeah.
Okay. Thanks.
Of course, SMA didn't go, so we actually
Yeah.
see if there's a second, third, but yeah, Jeff.
So I was kind of expecting that your last slide would show the movie that you would anticipate we would see, right? Because you've got this model, you've got the radius, so what does it look like? And because there's been a rich history of making movies and describing what we might see. I mean, Avi and Avery did this a long time ago, the EHT has done it. So what does this look like?
You mean like horizon scale?
So if we were to catch this flare with the EHT, what would it look like?
I will.
Or with or with
gravity.
gravity. I mean, gravity claims to have seen some. So how does it compare? That's
Off the bat, I don't know. We didn't do that calculation. It's interesting to do for sure.
What was your best fit orbital radius?
I thought
6, which is already
not very different
from
from
gravity.
gravity. Gravity was about 8.
Yeah, it's because the first author is gravity.
Yeah, so that's right. It comes out. It's
Also, these are all Keplerian orbits, right?
Keplerian, yeah.
So are you terminating your fifth region at the ISCA?
No.
Wait, sorry, was that 6 Schwarzschild radio or 6M?
Schwarzschild.
I see, sorry,
12M.
never mind. Okay,
12M.
okay, thank you. That will keep tripping me up.
It's not the ISCA.
It's not,
Quite far. out.
no,
It's really far out.
Yeah.
Yeah.
This goes 3 if it's not spinning,
And what's the orbital time there?
and 30. Again, numbers I should know off the top of my head.
You're assuming zero spin because
We
Yeah.
assume zero spin. in this
the orbital period at the ISCO
The
for a zero
25
spin is
minutes.
already half an hour. And that's kind of what that is, right?
Yeah.
Yeah, but this is farther out.
Is it retrograde? Is it retrograde?
No, no, there is no spin.
This is at 12 range. This is with 6 shorter radius.
That's the radius.
Yeah.
Yeah.
So this guy is like much further out than the.
So what's the orbital
How come
time?
that? Because the
3 hours.
for a zero spin, the ISCO period is half an hour.
This
Yeah.
is RG, this is RS.
Yeah, sorry, you guys are loudly agreeing with each other.
Ah,
The orbital period should be slower than 30 minutes, but this looks like
Longer.
Longer. This should be an hour and something, an hour and a half or
Yeah,
something.
I would imagine it would be, it's almost linear in that regime.
So
So,
it looks like maybe 45 minutes to me, which seems a little short for this rate.
yeah, it seems that, yeah.
But the
Just peak to peak
data
is a
looks
full
like
orbit.
30 minutes, right?
Which one?
Peak to peak is 30 minutes.
But does peak to peak indicate a full orbit?
Yeah,
Okay.
that's
Yeah,
the
but
Doppler,
It
right?
seems like
I
it's
guess
too
it is.
fast.
That
right?
is Doppler,
Seems
it's
like
30 minutes.
So then that
It's
is
too
fast.
fast.
Yeah.
It's a little short.
Yeah.
So it does seem maybe not crazy if it's RG and not RS.
Was
So
the
who's
first
loud
author off
thinking?
by a factor of 2?
My point is that that's a worthwhile calculation.
No, I think gravity is also at 11 m or so. They say 5.5. Shorter radius. So so then gravity would also have to be.
Well, I think maybe we have some homework to do.
So it would be substantially longer than 30 minutes.
It's possible that this was RG rather than RS. you
That's
see.
Yeah,
what
yeah,
they were
yeah,
not,
yeah.
that's what they're trying to figure out.
That's
Yeah.
17 degrees that's really split.
That is the kicker.
What's your best fit? What's your best fit for me?
Okay, well, we're past the hour and we have a lot to chew on here. So
I have one question before you guys close.
Okay, sure.
That near camp data, right? You had one nice
Yeah.
humongous flare, right? Was there by any chance submillimeter observations?
For this one, 2024,
Yeah,
no, we
unfortunately.
had radio.
Okay, radio. What did it do?
Right?
What did it do?
Good question. April 7th, is that this day or?
What they-
Oh, it's like, this is July.
It's April
That's the
7th.
5th, yeah,
Oh, it's
now it's the
April.
wrong.
Yeah,
When was the issue?
EST should have been looking at it.
Well, no, because
What year is this?
2024. So
2024.
this was in the window of the 2024 campaign, but
But not overlapping with
Not
the
overlapping.
issue.
Here is the
the
red,
MIRI did.
What,
Three
April
MIRI nights did, all
5.
3 JWST,
Okay.
April 5.
PhD nights. Yeah, this is the wrong, I could pull that up. I have it
Okay.
somewhere.
Wait,
But did it flare or not?
It's a time
Flare
delay
and delayed.
and delay.
It will be fascinating to take a look at that.
you can show it at the ITC lunch on Thursday.
Yeah, right, exactly. Yeah, leave out all the introductory stuff, all that, MIRI
Okay.
detector and all that. Yeah, show the good stuff.
I'm in pain, you have to be in pain too. right?
I understand, yeah.
All right, let's thank Joe.
Thanks, Joe.